Welcome to this problem walkthrough on LeetCode problem number 87, Scramble string. In this video, we'll dive into the problem, break it down, and explore different approaches to solve it. Whether you're preparing for a coding interview or sharpening your skills, you're in the right place. Let's get started. The problem asks us to determine whether one string, s2, is a scrambled version of another string, s1. Both strings have the same length, and s2 is considered a scrambled string of s1 if it can be created through a series of specific operations. These operations include splitting the string into two non-empty substrings, optionally swapping those substrings, and then recursively applying these steps to the resulting substrings. For instance, starting with the string great, we could split it into gr and eat, and then optionally swap them to get eager. This process can be repeated on each substring to create new variations. It's also important to note that a string is always considered a scrambled version of itself, without any operations. The input consists of two strings, s1 and s2, made up of lowercase English letters, and the output is a Boolean value, true if s2 is a scrambled string of s1, and false otherwise. To better understand the problem, let's look at the first example. Here, we have s1 is great and s2 is read. The output is true, and here's why. First, we can split s1, which is great, into two substrings, gr and eat. Then, we swap these two substrings, resulting in eager. Next, we focus on the substring eat and split it further into e and at. Swapping these two substrings gives us read, which matches s2. This sequence of splits and optional swaps shows that s2 can indeed be derived from s1, making it a scrambled string of s1. Now consider the second example, where s1 is ABCDE and s2 is caved. In this case, the output is false, and here's why. There is no valid sequence of splits and swaps that can transform s1 into s2. No matter how we split and rearrange the substrings of ABCDE, we cannot achieve the order of characters in caved. Therefore, s2 is not a scrambled string of s1. In contrast, in the third example, both s1 and s2 are just a. Since the strings are identical and only one character long, no operations are needed. This makes s2 a trivial scrambled string of s1, resulting in an output of true. The problem also comes with constraints and edge cases. The length of both strings ranges from 1 to 30, and they are always of equal length, consisting only of lowercase English letters. Some edge cases to consider include single character strings like s1 equals a and s2 equals a, which will always return true since they are identical. Strings with completely different characters, such as s1 equals abc and s2 equals xyz, will always return false because no rearrangement can make them match. For strings with the same characters but in different orders, like s1 equals abc and s2 equals cba, the result depends on whether a valid sequence of splits and swaps exists. Lastly, for larger strings near the upper limit of 30 characters, efficient implementation is crucial to handle the complexity of recursive operations without running into performance issues. To tackle the scramble string problem, the first approach to consider is the brute force method. The intuition here is straightforward. We generate all possible scrambled versions of the string s1 and check if s2 matches any of them. This involves recursively dividing s1 into two substrings at every possible index, swapping these substrings, and continuing this process recursively for the resulting pieces. The key steps are to split s1 into two parts, labeled as left and right, and then check if swapping these parts can produce s2 by validating the substrings recursively. However, the major drawback of this method is its inefficiency. The number of splits grows exponentially with the size of the string, leading to a time complexity of 4 to the power of n. While this approach is conceptually simple and easy to implement, it quickly becomes impractical for larger inputs due to the sheer number of recursive calls required. A more efficient way to solve this problem is by using recursion with memoization. This optimized approach builds on the brute force method but avoids redundant calculations by storing the results of previously solved subproblems. This is possible because the problem exhibits overlapping subproblems, a hallmark of dynamic programming. One key observation is that for s2 to be a scrambled string of s1, both strings must have the same frequency of characters. If their character counts differ, we can immediately eliminate s2 as a possibility. Beyond this, the solution involves recursively checking two conditions. First, whether the left part of s1 matches the left part of s2 and the right part of s1 matches the right part of s2. Second, whether the left part of S1 matches the right part of S2 and the right part of S1 matches the left part of S2, which represents a swapped configuration. Through memoization, we store the results of these checks, significantly reducing redundant computations. While this approach has a time complexity of n to the power of 4, and a space complexity of n cubed, it is still much faster and more feasible than the brute force alternative for strings of moderate length. The optimized recursion with memoization approach is the chosen strategy for solving this problem. It effectively balances simplicity and performance, avoiding the exponential inefficiency of brute force by leveraging memoization to cut down redundant calculations. The core insight lies in recognizing that scrambled strings follow a recursive structure, which can be systematically solved using a dynamic programming approach. This method is particularly advantageous because the brute force solution, though easy to implement, becomes computationally prohibitive as input size grows. By contrast, the optimized recursive strategy is much faster and well suited for the typical constraints of competitive programming, where string lengths are moderate, such as n less than or equal to 30. While the dynamic programming solution does require additional space for the memoization table, the trade-off is justified by the substantial reduction in time complexity. Overall, this approach is a practical and efficient solution for the problem at hand. The turning point in solving this problem was the realization that scrambled strings inherently follow a recursive structure, and that the problem's overlapping subproblems could be solved using memoization. This insight was the key to reducing the problem's complexity from exponential to polynomial. By systematically applying this approach, we arrive at a solution that is both practical and efficient. In conclusion, the optimized recursion with memoization method is the most suitable choice for this problem. It strikes a balance between computational efficiency and ease of implementation, making it ideal for competitive programming and technical interviews. While it isn't optimal for extremely large inputs, it is a significant improvement over brute force, providing a robust solution within the constraints typically encountered in real-world scenarios. In this problem, we need to determine if one string, S2, is a scrambled version of another string, S1. A scrambled string is created by recursively dividing a string into two non-empty substrings, swapping them, and repeating this process on the resulting substrings. For example, the string great can be scrambled into variations like reet or rete, among others. The task is to verify whether S2 could be one of these scrambled versions of S1. To solve this, we use dynamic programming with memoization. The core idea is to define a recursive function, is_scramble, S1, S2, that checks if S2 is a scrambled version of S1. There are two key base cases to handle. First, if S1 and S2 are identical, we can immediately return true because a string is always a scrambled version of itself. Second, if the sorted characters of S1 and S2 do not match, we return false, since scrambled strings must be anagrams of each other. These base cases allow us to prune unnecessary computations early in the process. To implement the recursive function, we partition S1 at every possible index and divide S2 into corresponding parts. For each split, we check two conditions to determine if the scrambling rules are satisfied. The first condition checks if the first part of S1 matches the first part of S2 and the second part of S1 matches the second part of S2. The second condition checks if the first part of S1 matches the second part of S2 and the second part of S1 matches the first part of S2. If either condition holds, we recursively verify the smaller substrings. To optimize this process, we use memoization by storing the results of previously computed function calls in a dictionary. This prevents us from repeatedly solving the same subproblems, saving time and reducing the algorithm's overall computational complexity. Finally, if any partition satisfies the scrambling conditions, we return true. Otherwise, after trying all possible splits, we return false. Breaking this down further, the problem is fundamentally recursive, as determining if S2 is a scrambled version of S1 relies on verifying smaller substrings recursively. This makes the problem a perfect fit for dynamic programming. A key insight is that we can prune unnecessary computations by first checking if S1 and S2 are anagrams. If they aren't, there's no need to proceed further, as non-anagrams cannot be scrambled versions of each other. Memoization plays a crucial role here by storing the results of previously computed string pairs, significantly improving efficiency and mitigating the exponential time complexity of raw recursion. From a data structure's perspective, we use a dictionary to store these results, where the keys are tuples of strings, and the values are booleans indicating whether the pair satisfies the scrambling condition. Additionally, the system stack handles the recursive calls, ensuring that each subproblem is processed in an organized manner. To further optimize the algorithm, the anagram check is implemented early and efficiently by sorting the strings, which eliminates non-matching pairs in O, n log n, time. Another optimization is early termination. As soon as a valid partition is found, the algorithm stops further checks and returns true, avoiding unnecessary computation for all possible splits. In terms of complexity, the time complexity is O, n to the power of 4. This comes from the fact that for every substring pair, we make it most n splits and compare substrings of length n, with an additional O, n log n, cost for the anagram check. The space complexity is O, n cubed, as we store results for all possible substring pairs in the memoization dictionary. Lastly, we handle edge cases carefully. For instance, empty strings are immediately invalid since scrambling requires non-empty strings, and single-character strings can only be scrambled versions of themselves if they are identical. Unequal string lengths are also invalid, as they can never produce valid scrambles. For deeply nested scrambles, memoization ensures that even the most complex cases are processed efficiently. Here, we start with the Python implementation of the Scramble string problem. The method isScramble begins by checking two simple base cases. First, if the lengths of the two strings s1 and s2 are not the same, we can immediately return false because it's impossible for them to be scrambled versions of each other. Next, if the strings are already identical, we know s2 is a scramble of s1, so we return true. Another quick check involves sorting the characters of both strings. If their sorted versions don't match, it means the strings don't even have the same set of characters, so we return false. After these initial checks, we proceed by defining a recursive helper function DFS and initialize a memoization dictionary to store the results of subproblems. The helper function will allow us to explore possible ways S2 could be a scrambled version of S1 by dividing and conquering smaller substrings. The recursion starts with the full lengths of the strings, and will build solutions for smaller segments as we go. The helper function DFS continues by first checking if the result for the current substring pair is already computed and stored in the memo dictionary. If it is, we return the cached result directly to avoid redundant computation. Then, we handle another base case. If the current substrings being compared are identical, we store true in memo for this substring pair and return true. On the other hand, if the sorted versions of the substrings do not match, we know it's impossible for them to be scrambled versions, so we store and return false. Now, we try splitting the strings into two parts at every possible position. For each split, we consider two cases: first, where the substrings are not swapped, and second, where the substrings are swapped. In either case, we recursively call DFS to check if the smaller parts match the criteria. If either case returns true, we store true for the current substring pair in memo and return true. If none of the splits work, we store false in memo and return false. Finally, the recursion starts with the full length of the strings by invoking DFS 0, 0, n from the isScramble method. Here, we begin implementing the solution for the Scramble string problem in Java. First, we define the main function isScramble, which takes two strings, s1 and s2, as input. The first check ensures that if the lengths of the two strings are different, we immediately return false, as they cannot be scrambles of each other. Next, we have a base case. If the strings are already equal, then s2 is trivially a scrambled version of s1, and we return true. After that, we check whether the two strings have the same set of characters by sorting their arrays and comparing them with arrays.equals. If the sorted arrays are not identical, it means the characters differ, so we return false. Finally, we initialize a memoization map to store the results of subproblems, which will help optimize our recursive approach by avoiding redundant calculations. The isScramble function calls a helper method DFS, which performs the recursive checks. This method takes indices I1 and I2, the length of the substring being checked, and the memoization map as parameters. To begin, we create a unique key for the current substring combination using the indices in length, and check if this key already exists in the memo. If the result has been computed before, we return the cached value, saving time. Another base case is handled here. If the substrings of S1 and S2 defined by I1 and I2 for the given length are equal, we store true in the memo for this key and return true. Then, we check if the sorted substrings are identical. If they are not, it means there's no way one can be scrambled into the other, so we store false in the memo and return it. This ensures that unnecessary recursive calls are avoided for invalid cases. Next, we attempt to split the current substring at every possible position, starting from one character onward. For each split point, we consider two cases. In the first case, the substrings are not swapped. If the left part of S1 matches the left part of S2, and the right parts also match, the current configuration is valid. In such a case, we store true in the memo and return it. In the second case, the substrings are swapped. Here, we check if the left part of S1 matches the right part of S2 and vice versa. If both conditions hold, we again store true in the memo and return it. If neither case results in a valid configuration for any split, we store false for the current key in the memo and return it. This ensures that we exhaustively and efficiently explore all possible splits while leveraging memoization to avoid redundant calculations. To begin solving this problem, we start with the example where S1 is great and S2 is regeat. The first step involves some initial checks. We confirm that both strings are of equal length, which is true since they each have 5 characters. Next, we check if the strings are identical, which they are not, as great is not equal to regeat. Finally, we verify if they contain the same set of characters by comparing their sorted versions. Since both strings share the character set, A, E, G, R, T, this check passes. With these preliminary validations complete, we initiate the recursion by calling the DFS function with parameters to compare the entire strings. From here, we attempt to split the strings at different points, starting with a split of 1. In this split, we analyze two cases: first, without swapping, where G from S1 is compared to or from S2, which fails. In the second case, with a swap, G from S1 matches G from the other end of S2, which succeeds, prompting recursive calls to further explore the remaining substrings. These recursive splits and comparisons continue until all subproblems are checked. After evaluating all potential splits and recursive subproblems, we determine that S2, regeat, can indeed be formed by scrambling S1, great. Thus, the function returns true for this example. Moving on to the next case, we examine S1 as ABCDE and S2 as caved. Similar to the first example, the initial checks confirm that both strings are of equal length, are not identical, but do share the same character set when sorted. With these validations in place, recursion is initiated to compare the full strings. The DFS function is called with parameters covering the entire range of both strings, and we proceed to evaluate possible splits. In this second example, we begin by testing a split of 1. In the no-swap case, A from S1 is compared to C from S2, which fails. In the swap case, A from S1 is compared to D from S2, which also fails. Since neither case succeeds, we move to the next split point, split equals 2. Here, we evaluate both the no-swap and swap scenarios, but again, none of the substrings from S1 match with the corresponding substrings from S2. After exhausting all possible split points and recursive checks, we find no valid configuration that makes caved a scramble of ABCDE. Therefore, the function returns false for this example. Now, let's examine the third example where S1 is ABCD and S2 is back. As before, the initial checks confirm that the strings are the same length, are not identical, but do share the same set of characters when sorted. With these checks complete, we initiate the recursion by calling the DFS function to analyze the entire strings. Testing begins with a split point of 1. In the no-swap case, A from S1 does not match B from S2, so this fails. In the swap case, A from S1 matches A from the other end of S2, which succeeds. This triggers recursive calls to further evaluate the remaining substrings, specifically BCD from S1 against BAD from S2. These recursive splits continue, with further comparisons and validations, until all subproblems are resolved. Through these recursive checks and valid splits, we confirm that BAD can indeed be formed by scrambling ABCD. As a result, the function returns true for this example. This demonstrates how the algorithm effectively handles cases where scrambling involves multiple levels of recursive splitting and reconstruction, providing the correct answer based on the structure of the strings. To analyze the time complexity of our solution, we start with the base case checks. First, verifying if the lengths of S1 and S2 are equal is a constant time operation, O1. Next, comparing the strings directly, S1 equals S2, takes linear time, O(n), because we examine each character. Additionally, sorting both strings to ensure their characters match contributes O(n) log n, due to the nature of sorting algorithms. Since these checks are performed only once, their cumulative contribution is O(n) log n. Moving on to the recursive calls, the function dfs, I1, I2, length, is invoked for various substrings. For a substring of length, we try all possible split points, ranging from 1 to length 1. At each split, 2 recursive calls are made, one for the scenario where the substrings are not swapped, and another for when they are swapped. This results in approximately 2 length 1 recursive calls for a substring of length. Now, memoization plays a crucial role in optimizing the solution. By storing results of subproblems in a dictionary memo, we avoid redundant calculations. The number of unique subproblems is determined by the triplet, I1, I2, length, where I1 and I2 can each take n values and length can range from 1 to n. This gives us n cubed unique subproblems in total. Each subproblem involves sorting substrings, which takes n log n, and performing recursive calls. However, thanks to memoization, each subproblem is only processed once, avoiding unnecessary recomputations. When we combine the total number of subproblems, n cubed, and the work done per subproblem, n, the overall time complexity of the solution becomes n to the power of 4. Turning our attention to space complexity, the recursive stack space is the first contributor. The depth of the recursion tree is proportional to the length of the strings, n. In the worst case, this depth reaches n, adding n space. Next, the memoization dictionary stores the results of all unique subproblems. As we calculated earlier, there are n cubed unique subproblems. Each entry in the dictionary requires constant space, O1, making the total space used by memoization n cubed. Sorting substrings also requires additional space, specifically n, for temporary buffer storage. However, this is transient and does not contribute to the overall persistent space complexity. When we consider all factors, the space complexity is dominated by the memoization dictionary, resulting in a total of n cubed. Comparing this optimized approach to a brute force solution highlights its efficiency. A naive approach would involve generating all possible scrambled versions of S1 and checking each against S2. Generating all permutations of S1 alone requires n time, and comparing each permutation to S2 adds an additional n for each check. This results in an infeasible total complexity of n for larger inputs. In contrast, the optimized approach uses recursion and memoization to reduce the problem space significantly. With n cubed, unique subproblems and an overall time complexity of n to the power of 4, this solution is orders of magnitude more efficient than the brute force method. Considering the best, average, and worst cases provides further insight into the solution's behavior. In the best case, if S1 and S2 are identical or if their character counts don't match, the function exits early after the initial checks. Here, the time complexity is n log n, dominated by the sorting step. In the average case, the recursive calls typically involve balanced splitting of the strings, and memoization prevents redundant calculations. This results in a time complexity of n to the power of 4. The worst case occurs when every split requires full exploration of both swapped and non-swapped scenarios, leading to the maximum number of recursive calls. Even in this situation, the time complexity remains n to the power of 4. The mathematical proof for this is grounded in the fact that the number of subproblems is bounded by n cubed, and each subproblem involves n work for splitting and recursion. Similarly, space complexity is dominated by the memoization dictionary, leading to n cubed space usage. When tackling the Scramble string problem, there are a few common pitfalls to watch out for. First, many people confuse this with a simple permutation check, where they only compare the frequency of characters. However, this problem is much more nuanced because it relies on the structural rearrangement of substrings, not just the character counts. The order and recursive splitting of substrings are critical to determining whether one string is a valid scramble of another. Another mistake is attempting a brute force approach by generating all possible permutations or scrambled combinations of the first string and comparing each to the second string. While this might seem like a thorough method, it quickly becomes computationally infeasible due to its exponential time complexity. Lastly, edge cases are often overlooked. For example, strings of different lengths, empty strings, or strings with repeated characters can introduce subtle bugs or runtime errors if not handled properly. It's essential to account for these scenarios in your implementation to ensure correctness and robustness. Another common challenge arises with dynamic programming solutions. Specifically, initializing the DP table incorrectly, especially for the base case of single character strings, can lead to cascading errors throughout the solution. Proper initialization is key because the DP table builds upon these base cases to handle larger substrings. Additionally, some implementations fail to optimize recursive calls by not using memoization. Without memoization, you end up recomputing the same subproblems multiple times, leading to a dramatic increase in runtime complexity. Beyond these technical issues, it's important to approach this problem strategically during interviews. Recognize the recursive partitioning pattern, which involves splitting the string and testing both the swapped and unswapped orders. Think of this as constructing and exploring a tree of substrings. Interviewers often expect you to transition from a naive recursive solution to a dynamic programming approach, so highlight how memoization reduces redundant computations. Don't forget to discuss edge cases and analyze time complexity, explaining the trade-offs between naive recursion, memoized recursion, and iterative DP, where the optimized solution typically has a complexity of n to the power of 4. This problem has strong connections to other dynamic programming challenges, which can help you recognize patterns and apply transferable strategies. For example, LeetCode 10, regular expression matching, is another problem that requires careful handling of substring patterns using DP. Similarly, LeetCode 97, interleaving string, involves checking how one string can be formed by interleaving two others, employing a recursive and dynamic programming approach. LeetCode 44, wildcard matching, focuses on pattern matching and also emphasizes handling edge cases effectively. Lastly, LeetCode 583, delete operation for two strings, is another string manipulation problem that relies heavily on dynamic programming. As you work through these related problems, you'll notice recurring techniques and concepts that can strengthen your understanding of how to approach Scramble string effectively. For alternative solutions, starting with a recursive approach combined with memoization is often a good stepping stone. While it may not be the fastest for larger input sizes, it's easier to implement and debug, making it a great way to build your understanding of the problem before transitioning to more advanced techniques. Dynamic programming, while more complex to set up, is the go-to solution for larger input sizes. It provides the best performance, with a time complexity of n to the power of 4, and is particularly useful when optimization is critical. This approach works well when you've already mastered the recursive solution and are looking to make your implementation more efficient. Another potential method is substring hashing, which can reduce comparisons between substrings by generating unique hash values. However, this approach is significantly harder to implement and maintain, making it less common for this problem. It's typically only used in specific variations where hashing provides a clear advantage. Overall, understanding the trade-offs between different approaches will help you choose the right strategy based on the problem constraints and input size, ensuring you can effectively solve both standard and related variations of the Scramble string problem. Great job making it to the end. We reviewed the problem, explored the solution, and discussed key takeaways. Remember, practice is the key to mastering these techniques. If you enjoyed this video, don't forget to like, subscribe, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!